Hi students. In this lecture, I am going to discuss previous year's IIT questions based on Motional EMF and Faraday's law. Let us see first one. Let's see the question given. The variation of induced EMF with the time in a coil if a short bar magnet is moved along its axis with a constant velocity is best represented as, and you can see graphs here and see how to get the answer, means how to decide which graph is the correct one. And if you observe carefully, up to some time, this is approaching the coil. That means flux through this coil is increasing. So initially, because of increase in flux, EMF is induced. And you can see after some time, this comes out of the coil. So while it is coming out of the coil, means moving away from coil, then because of decrease in flux, EMF will be induced. That means initially because of increasing flux, now it is because of decreasing flux. That means, let us see here once. For example, just imagine in the place of that coil, just imagine like this. There is a one conducting loop, a conducting loop like this. Now this is magnet. So initially what we can do is here, because of the approach of the magnet, that means flux through this coil will increase. Because of that, current flows in the coil. And after some time, this will move away from the coil, right? Now it is because of decreasing flux, current flows. So in first case, because of increasing flux. Second case, it is because of decreasing flux. That means direction of current changes, right? Direction of current change means you can think like this. Suppose this is a battery. This is now resistor. Now current flows in this. It is anti-clockwise, right? Current flows here, it is anti-clockwise. Suppose if I am replacing the battery now, or if I am reversing battery, that means it is now like this. If you reverse battery, now current flows, it is clockwise. That means you have to understand that direction of current change, it means you can say the polarity of the battery changed, like this is a plus minus, it is now reversed, minus a plus. The meaning of direction of EMF changed. Okay, so like this we can say initially while approaching direction of current, while receding direction of current, they are opposite. That indicates the direction of EMF in the sense that the polarity is now changed. And if you see graphs, you can see here, first one, throughout there is no change in polarity of EMF, means it remains positive throughout the motion, and that is not correct. And here also, throughout the motion it is positive, and here also it is throughout the motion positive only. But if you observe, coming to graph B, up to some time it is negative, and after that it is a positive. So sign has changed, or you can say direction of current reverses, right? That means correct option is B. Okay. Let us see next one. A circular loop of radius r carrying current I lies in xy plane with its center at origin. Condition given, circular loop of radius r carrying current I lies in xy plane with its center at origin. The total magnetic flux through xy plane is, and you can see options directly proportional to y, directly proportional to r. Okay, let us see how to decide this. So the condition given: circular loop carrying current. It is in xy plane, center is origin. So we are taking a circular loop, center is origin. This is now xy plane, right? Now we can see current is flowing. In this, current is flowing. That means now this board plane is xy plane. Board plane is xy plane. Current may be clockwise or maybe anti-clockwise. Okay. The total magnetic flux through xy plane is. So first we have to focus on how field lines are. Okay. We are knowing that at center field lines, or you can see direction of field at center. It is normal and towards us, right? See carefully. If you curl fingers of right hand along the current flow, thumb of right hand will be towards us. So at center, field is now towards us. And if you observe now, taking a small part, taking a small part, then see because of this current carrying where field lines, or you can see I'm drawing separately that small part. So I have taken this, take it as AB, a small part on the back. This is A. And see direction of current. It is now like this. Now just because of this, left of this one, left of this field lines, or you can see direction of field, it is towards us, right? So left of this wire, because of this wire, field is towards us, means normal to this board plane and towards us. And if you take right of this wire, field is now into the board. Okay. So it is now towards us. I'm showing as dot circle. It is now into the board. That is a cross circle. That means we have to keep in mind field lines here entering xy plane, and here field lines leaving xy plane. I'm repeating. Here direction of field into the board, and here direction of field outwards towards us. That means here field lines into the board, here field lines towards us. And we are knowing that magnetic field lines are closed curves, right? So how many field lines are entering this xy plane? How many field lines leaving this xy plane? Both are same. So number of field lines entering, number of field lines leaving that xy plane, both are same. How we are knowing this means because magnetic field lines are closed. Okay, they are not open just like electric field lines. So we have learned that electric field lines are open. They start from positive charge and end on negative charge. You can see here, suppose positive charge and this is negative charge. They start from positive charge and end on negative charge. So they are open curves. But coming to magnetic field lines are closed. There is no starting point, no ending point. That's why here number of field lines entering xy plane, number of field lines leaving xy plane, both are same. Therefore, total magnetic flux through xy plane is 0. Okay. So I hope you got a clarity. Let us see next problem. A metallic square loop ABCD is moving in its own plane with velocity v in a uniform magnetic perpendicular or uniform magnetic field perpendicular to its plane as shown. And you can see here given dots. Dot means towards us and normal to this board plane. Okay. Electric field is induced, right? And you can see options in AD but not in basic. Okay. Let us see first how to decide. First of all, make the given diagram. Let's see what is given here. It is a metallic square loop. Metallic square loop. It is now moving. A, B, C, D. Field is now normal to this board plane and towards us. Velocity given it is V. Let us consider this board plane as XY plane. Right now, see what he's asking here. Electric field is induced. So first thing what we can say is magnetic field is present everywhere in this plane, right? That means because of this motion of the loop, net EMF in the loop is zero. The first point what I'm concluding here is net EMF E, A, B, C, D in this loop is zero. Okay, because due to motion of this loop, flux through this loop is not changing, right? But if you observe motion EMF, it is L bar dot V bar cross V bar, right? Now I am using this one for each side. If you see AB, L bar and V bar, they are parallel for AB and CD. If any two vectors are parallel, no EMF is induced. So for AB and CD, 0. Okay. Now coming to AD and BC. We can see this AD and BC. L bar, V bar and B bar. All three are mutually perpendicular. Right? That means it's a modulus value. If I am focusing EAD or it is EBC, both are same. That value equal to BLV if this side length is L. Okay. Right. Now see options. So we have EMF only across ED and across BC. Right. That means electric field is induced in AD and BC. You can see option D. Okay. And in the same question, they can ask like out of A and D, which is high potential and which is low potential. Okay. Already we have discussed questions like this. So I'm explaining once again. I am focusing force equation F bar equal to Q into V bar cross V bar. Let us focus AD. Okay. So I am focusing AD. Now in that I am focusing electrons because now electrons are moving, right? We can see velocity. It is in which direction? Velocity is along positive x-axis, right? So I am focusing force on electrons. Therefore, charge is minus velocity. Velocity direction is now I cap. I cap. Field is now towards us. That is K cap. So I cap cross K cap. That is minus J cap. And minus is present. It is now J cap. Okay. That means on electrons, force acting is along positive y-axis. That means they will move, or you can say they will accumulate at this end. So this end becomes now positive. So out of AD, which is high potential, means D will be high potential and A will be low potential. Now same thing applies for BC also. Okay. So if we draw this one with equivalent batteries, see how to draw. I have to place a battery here. That should be like this. That battery should be A is low potential. So A is low potential and D is high potential like this. Coming to here also same logic. This is low potential and this is high potential, right? Now you can see if you have two identical batteries, now in this loop, what is net EMF? That is equal to zero, right? Directly we can say that. Okay. Let us see next problem. See the question given. A metal rod moves at a constant velocity in a direction perpendicular to its length. A constant uniform magnetic field exists in the space in a direction perpendicular to the rod as well as its velocity. Select the correct statements from the following. Actually, we have solved this question earlier also. Let us see now. First of all, see, first make a diagram. Given metal rod moves with a velocity. It moves with a velocity. Condition given that velocity perpendicular to its length, like this. And given field perpendicular to rod as well as its velocity. Let us take it as into the board. Right. Then you can say an EMF is induced across the ends of the rod. And EMF is induced across the ends of the rod. Right. Now see options. The entire rod is at same electric potential, but is wrong. Okay. Because EMF is induced. Even you can say here in which direction electrons flow. Right. So taking this is X and this is Y. F bar equal to Q into V bar cross B bar, right? Focus electrons, charge negative. Direction of velocity, it is I cap. V bar minus K cap. So minus minus plus. Remaining I cap cross K cap, that is minus J cap. Electrons accumulate at end B. This is low potential, this is a high potential. So all points not having same potential. So option A is not correct. Next, there is an electric field in the rod. Yes, it is correct. Because of accumulation of electrons. Now there is an electric field, right? So option B is correct. Next, the electric potential is highest at the center of the rod and it decreases towards its ends. That is wrong. A is high potential, B low potential. As we are moving from A to B, potential decreases. Okay, that's why C is wrong. Of course, D also wrong. The electric potential is lowest at center and increases towards ends, and that also wrong. Okay, so correct option is it is option B. Okay, right. Let us see the next problem. The figure shows certain wire segments joined together to form a coplanar loop. The loop is placed in a perpendicular magnetic field in the direction going into the plane of the figure. The magnitude of the field increases with the time. I1 and I2 are the currents in the segments AB and CD. Then we can see diagram here. There is a one loop. And here you have to focus now, this is small gap is there. That is very important to decide the options which are correct. Now see what he's asking. Like option A, I1 greater than I2, I1 less than I2. But remember, here current flows. We can say, for example, A to B, A to B, then flows like this, D to C in this way. That means there is only one current is flowing in these wires. So first conclusion, I1 equal to I2. In fact, there is only one current. Okay, there is no I1, no I2. That means according to the notations given, I1 equal to I2. That is the first thing what we have to understand, right? Next one, how this current is flowing. Is it like A to B? If I am saying A to B, then it is now D to C, right? If you say B to A, then it is B to A means it is now C to D, right? We can see option C and option D. So now we have to verify which is the correct one. Okay, let us see how to decide. So first of all, make the diagram given. So you have to focus here. This end is not closed. Okay, next. So coming to here, it is now like this, right? Now observe carefully. Here loop in the sense, field is into the board. This is given as A and this is B, C and D. So loop. Remember, this is not loop because this is open here. Okay, this is not loop. Loop means only this part. This is now loop. Okay, what I'm showing here. This is loop. This inner part. Or I can show like this. Loop means here. I'm shading here. This area we have to focus. Flux, how it is changing in this part of the area. This is closed, not this one. Okay, right. Now focus in this part which I'm shading here. In this part, how flux change. Condition given that here magnitude of the field increases. Here V value strength is increasing. So flux through this area is increasing. Therefore, flux through this area. So now we have to focus because of induced current. Because of induced current, magnetic field is induced. And because of that magnetic field, it has to oppose this increasing flux. That means magnetic field due to induced current must be opposite to this field. Okay, that means now field due to induced current must be towards us. So keep the thumb of right hand towards us, curl fingers. Okay, keeping right hand, thumb of our right hand towards us and curl fingers. Now curling fingers, they are anti-clockwise. So current must be anti-clockwise, right? Now see what I am saying here. Suppose I am focusing from C to D. If I focus C to D current, because of this, at this location, field must be outwards. Okay, check once. If I am taking C to D at this location, I am drawing separately. This is now D and this is C. At this location, field must be outwards. If I am taking current is now C to D, field is now outwards. See carefully. If I am taking current C to D, if I am taking current C to D, Then because of this current field below this wire is towards us, right? Next, if current flows from C to D, now see carefully C to D, current flows like this. Then it is now current flowing from A to B, A to B. This is A and this is B. C to D means current is now A to B. It flows now A to B. If current flows from A to B, above this wire, field must be outwards. Again, keep the thumb along current flow of your right hand and see curling fingers. The field is now towards us at this location. That means it is now opposing the increasing flux. That means correct option is now. Correct option is I2 is from A to B. Sorry, I1. I1 is in the direction of AB. I2 in the direction of CD. So option D is correct one. Okay. So most of the students getting confusion like they're focusing this loop. But remember, this is not a loop. This is open. We have to focus only this loop. Then we get a clarity on how to decide direction of current. Okay. So I hope you got a clarity.